Now, do you remember when I said that translation is a fussy little bitch? Well, let's do a little recap here. Let's count the ways in which it is a pain in our butt. So, scaling. When you scale, you obviously have to, well, here we're doing drawable, right? So when you apply a scale to a drawable object, you obviously have to apply that to its internal scale variable, but you also have to apply it to the translation. And when you rotate, you've also got to apply that rotation to the translation. You don't have to, when you scale, you don't have to do anything for rotation. When you rotate, you don't have to do anything for scaling. And when you translate, you don't have to worry about scale or rotation. It's only in the other guys, you've got to worry about translation. Everything else you do, you've also got to do a little special thing for translation. It's a very high maintenance girlfriend. I mean, transformation. So it shouldn't be super surprising to learn that we can't actually represent a translation in a 2x2 matrix. For a 2D translation, you're not going to fit that in a 2x2 matrix. It's not possible. And the reason why is, well, when you think about it, where we got this translation X, translation Y, and we want to have a matrix transform such that the result is X plus TX and Y plus TY. So what do you got to put in here to get that? Nothing is going to work. And the reason why is, if we put, let's say, TX in here, TY in here, well, first of all, that's going to be your mother trucking scaling separately for X and Y, basically. But the thing is when you do this, you're going to get X times TX, and that's not what you want. But I mean, what else are you going to do? Well, you could say, well, we want X plus TX. So we'll put the TX in there, and there's a TY in here, and we'll put 1. So sure, if you multiply, here you go, you got 1 times X, that gives you your X. So far, so good. Next one, TX times Y. So you're scaling your translation by your Y, and you don't want to do that. Your Y is going to frick over your translation. So because these X and Y are going to be multiplied in here, you're not going to be able to get just the pure addition of TX and TY, and that's why it doesn't work. Let's prove it a different way here. So we've got a vector, it's at the origin, and we want to translate it up and to the right by 5. So we want a result of this. So what values do we got to put in this matrix in order to translate this from 0, 0 to 5, 5? Well, the answer is it's impossible, right? There's no values that you can put in here to get this result, because 0 times anything plus 0 times anything else is going to be always a big fat 0. It's impossible. And so because we've just proved that we can't translate the origin, that means that in general, it's not going to be possible to create a 2x2 matrix to encode a translation. So what the hell are we going to do? Do we just give up and say, okay, we just have to add a vector after we apply our matrix transformation? There's no other way to it? No, never give up. Never admit defeat. There is a trick that we can do to enable us to put all of our transformations in a single matrix, and then we are able to apply them all in one shot. And that trick is we actually have to encode our 2D transformation in a 3x3 matrix. So we add an extra element in there, an extra row and column, and that gives us the space we need to encode the fussy little bitch's information into that bullshit. So how does this work? Well, we know that when we're doing vector by matrix multiplication, dimensions have to match. So our vector is going to have to be 3-element vector. And you might be wondering, well, we got X, we got Y. Remember, we're in 2-dimensional space. There's no Z. What is the third element going to be? And here's where the main trick comes in. We set that to 1. That is going to always be 1 for our 2D coordinates. So now we have this 1 chilling out in here. And this is going to enable us to select the third column. So let's do a simple translation. So for translation, we don't want to scale X or Y. We don't want to do anything with them. So that means let's fill in here our identity matrix. So far, so good. Now, when we are mapping our input vertex into X, what we want to have here is X plus TX. So we want X times 1 plus Y times 0 plus TX times 1. And that'll give us our mapping. And then here, ty times 1 will give us y plus ty. And then 0, 0, because we don't want x or y in here, we just want 1 times 1 that will maintain the 1 in the third column, because we want to keep that 1 there. That 1 is very important for selecting our translation guys to put them in here. Beautiful. So this is the trick. This is the dirty little trick. You have to increase your dimensions of your matrix and your vectors by 1, but that will allow you to now encode translation inside of the same matrix that's also encoding scaling and rotation and flipping and other stuff. Now you might be wondering what we call this 1 here. I mean, normally if you have a 3-dimensional matrix, it's x, y, z, right? A 3-dimensional vector. But this isn't really a z coordinate in the traditional sense of 3-dimensional space. And what we actually tend to call this is w, because, well, this same trick, it applies to 3-dimensional graphics as well. So when you have 3-dimensional graphics, your normal matrix for transformation is going to be 3 by 3, but if you want to get translation in there, you have to have a 4 by 4 matrix, and your vectors have to be 4 by 1. And then your vectors are going to be x, y, z, and the fourth component is called w in this case. And you may have seen this if you've looked at any kind of material on 3D graphics. 3-dimensional vectors, generally, they often get 4 coordinates for the reasons stated above and for other reasons, and the fourth guy is called w. But that, my friends, is going to be a story for another day. Now let's do this stuff up in code, shall we? First thing we need to do is we need to convert this mate2 into a mate3. So I'm going to rename this dork here, and we're going to rename all the stuff in here, so give me a second. So mate2 becomes mate3 with a little find and replace, and here now cells are going to be 3 by 3. Fair enough. Okay, now we need to change. Well, first off, we're not going to be able to multiply vec2s anymore. We need vec3s, which we're going to create in a little bit. Now we need to expand this multiplication here to facilitate the extra element. And we're going to call that extra element, we could call it z. That's normally what you would call the third element of a vec3. But we're going to call it w to signify that it's not the z of 3-dimensional graphics, it is the special w for doing our bullshits. So that fixes it right there. And now we've got to handle the multiplication, which is incredibly simple because we've done it with a loop already. It's all dynamic. All we've got to do is change this from 2 to 3, and matrix multiplication should be all done up very nice. We need to upgrade the dimensions of all of our factory functions for creating transforms. And that's going to look like this. We just put in the diagonal here, we put a 1 here, and the rest are just all zeros. And last but not least, let's add a new function to generate a translation. And that's very simple, just 1s on the diagonal, and then x and y in the places where I showed you. And there we go. This should be our mate3, our 3-dimensional, our 3 by 3 matrix for 2-dimensional space, all jiggered up. That's not a bad word, trust me. Please don't demonetize me, Google DeepMind. All right, now for the vec3, I'm just going to copy vec2 and then mostly just do find and replace. So we do the find and replace. Now things like length, normalize, get normalized, they're not going to take into consideration w, because w doesn't really factor into the length of the 2-dimensional vector itself. Rotate is the same, it doesn't affect w. Get rotated, operator multiply. I'm not going to make this one affect w either. We could, but I don't think it's necessary. For operator equals, we do want to copy over the w, but for plus and equals, we just leave w as it is. Minus and equal, leave it as it is. Plus, leave it as it is, leave it as it is. Leave it as it is, leave it as it is, leave it as it is, leave it as it is. Don't consider it when doing comparisons. And that should be good, because no matter what, we always just want to set this guy to 1. So we'll just set it right down here, and that'll save ourselves some effort. Now I do want to be able to convert from a vec2 into a vec3 and vice versa. So we do that by doing a constructor that takes vec2, it's explicit, and we do a conversion operator So we can convert to vec2, also explicit, and just return x and y. So we can see here that vec3, its w parameter is set on construction and then it's never touched. Now in three-dimensional graphics, w is not always going to be 1. There will be situations where it'll be different than 1. I mean, you could have that for two-dimensional graphics as well. It has to do with projection, but we're not going to be dealing with that here, so we can just set it always to 1 and forget about it. We'll include vec2.h up here just to be safe. And then if we go back to mate 3, we should be out of the red. Now, whether it compiles or not is a different, that's a different bag of worms, isn't it? But let's try something out here. So we'll change this to include mate 3 in game.cpp. And please stop. Yeah, okay, good. And now we can do rotation, scale, flip. And let's add a fourth transformation, which is our translation. I'm going to concatenate them all together. So far, so good. Now we've got to apply that to all the vertices. The only problem is our vertices are vec2 and our matrix is a mate 3. That's not going to work. So what we got to do is we just got to do a little bit of conversion in here. It's annoying, but it's got to be done. So the idea is we convert v to this v vec2 into a vec3. We do the multiplication. We convert that back to vec2 and assign it back to v. Seems to be complaining. Let's look at vec3. Explicit operator underscore vec2. Okay, that's not correct. It's got to be vec2 of t. Vec2 of t. There. Go back to game. And now everyone's happy. Build. See if it actually builds. Probably not. I was wrong. It did build. And then we run it. And we see that we are translated up and to the right by what appears to be about 100 pixels. Pretty damn sweet. This is actually more verbose than it needs to be. No problem. Okay. Now, here's the interesting thing. Remember, if you apply a rotation to a translation, the translation gets rotated. So if you apply a translation and then afterwards you apply a rotation, it's going to rotate that translation. If you apply a scale afterwards, it is going to scale that translation. But our translation is not being rotated or scaled. So that shows us one thing, and that is the order of the transformations that are applied goes from right to left. So first we're going to do a rotation, then we're going to do a scale, then we're going to do a flip, and finally we do the translation. What happens if we do the translation first? We see that our translation gets rotated and then it gets flipped, and it also gets scaled. It's farther off now. It's going off the screen actually. This gives us many things to think about and to remember and be careful about. First of all, when you're working with translations, the order matters, just like it mattered before. When you're concatenating matrices, the order in which the concatenation happens matters when you're dealing with translations. So you put it here, all of these are going to be applied to the translation. Let's cut this out, and we're going to put the transform 2 and 3 before this one. So now it's going to do the scale and the flip, then it's going to translate, then it's going to rotate. So now only the rotation will be applied to the translation. We should see it, yep, up here. So before it was more like over here, but that got rotated. But the flip and the scale were not applied to the translation. So remember, order matters when you're concatenating matrices, at least in terms of translation, and goes from right to left. It's probably more intuitive to think of it in terms of this one, then this one, then this one, then this one, left to right, but it is right to left. That's the way it goes. Think of it, it's being applied to this vertex. So the vertex comes here and it's applied this order, this, going from right to left. Remember, right to left, that's the order in which your transformations are going to be applied in this matrix concatenation. All right, in this setup here, I've got a translation matrix and I got a rotation matrix, and I'm going to concatenate the two of them. Now, look in here, we can see our translation matrix right here. It's got the ones on the diagonal, it's got your 6 and your 9. Those are your two translation values. And when I concatenate them here, rotation is on the right, so it's going to happen logically first. So this is a rotation followed by a translation. And if we step over this, we can see that, yeah, we've got the rotation stuff in here. It's the same. And to that has been added the translation stuff. Wasn't in here, but it's in here now. And that makes sense, right? Because a rotation should not be affected by a translation. But let's swap these guys now. So now we got a translation followed by a rotation, and when we step over, we can see here that our translation values have been modified. They are different now, and that makes sense, right? Because if you do a translation first and then you rotate, you're going to rotate that translation, and that's what we're seeing here. It's the same rotation as before, but the translation has now been affected if you swap the order of multiplication. Now you might think that increasing the dimensions of all your matrices and all your vectors is kind of a dumb little hack just to shoehorn in translation into your transformation matrices, but actually there is a whole sub-branch of mathematics that deals with this stuff. It's got a theoretical basis for why this is a thing that you can do. It's not just a hack. And the name of this topic in mathematics is called projective geometry. So this is a deep rabbit hole to dive into. And I'm going to tell you, for most people, the juice probably ain't going to be worth the squeeze. You can do three-dimensional graphics just fine without worrying about learning, all the theory behind projective geometry. But if you really like math, by all means, go ahead, try to study up on it. It certainly can't hurt, and will probably help you understand 3D graphics a little better. I'm just saying that for most of you, probably not going to be worth it. All right, now let's renovate the Starfield pipeline to use matrices instead of what we've been using so far, which is just a separate rotation angle and scaling factor and translation. So we're going to use matrices, and that's going to be a pretty big renovation. There's going to be lots of changes. The first choice that we have to make is, what are we going to do about our vectors? Because in order to use transformations with our mate 3, our vectors are also going to have to be vec3. But I don't want to change all the stuff from vec2 to vec3. That's a lot of stuff to change. So instead, what we're going to do is we're going to leave everything vec2. The only place where we really need vec3 is when we're multiplying by our matrices. So what I'm going to do, well, there's a couple of ways that we could handle this. One way is that we could change our multiplication function so that it just imagines that there is a 1 in the third element. So it'll take a vec2 and it'll imagine that there's an extra element there. The other way is simply to take a vec2 and convert it to a vec3. And that's what we're going to do, because that's easier. And there you go. So now, when we multiply any two-dimensional vector by our mate 3, what we're going to do is we're going to convert that to a vec3, which is going to add a w equal to 1. Then we're going to do the multiplication. We're going to convert back to vec2 and return it. So a very important part of the drawable pipeline is the drawable object. And we can see here where the buck stops is draw close polyline. That gets past all the transformation stuff, and that's where the transformation actually gets applied to each vertex. So let's go to this guy. Now what we're going to do is we're going to rework this. We're going to make it take a single transformation matrix. And we need to know about mate 3, so let's include that, and you're happy. Good. Okay, now we can continue with the doings. So we don't need any of this stuff because all this sine and cos, that's all been encoded in the matrix. We don't need this anymore. Go away. So front is equal to verts.front times our transformation. So whenever we see xform, we replace that with times transform. Transform times this. And that's pretty much it, I guess. That's it. Yeah, there you go, there you go, there you go, there you go. You're done. That should work. We will see if there's anything else that I missed, but that seems like it works. This is much cleaner, much shorter. This is more beautiful. Everything is happy. We're all happy. We're all stars in the dope show, etc. Now, back to our important player, drawable. Render is now going to be rendered a little more sexier. First of all, we're not going to store all these guys separately anymore. We're just going to store one transformation. So let's go mate 3 transformation. And then in here, transformation. And that should fix that. Now, for translate, scale independent, and rotate, we're going to need to do a little different stuffs in here. So scale independent, the only reason we put that in there was to do the flip. So let's change this into flip Y. I could add independent scaling into our matrix. And you know what? Screw it. Let's put independent scaling into the matrix to make it fit this instead of making this fit the existing matrix. So I'm going to add another transformation. Scale independent, and that's going to be the scaling of X and the scaling of Y. And so we just put X in here. We put Y in here. These boys got to go to 0 and 0 and you're 1. So here's scale independent. Now we can use that where? Here. Okay, so let's do all these guys into our stuff. So a drawable, when you create it, it should start off with a mate3 equal to mate3 identity. Because you want it to start, if you initialize it to all 0, no matter what you concatenate, what you multiply in, the result will always be 0. You want to initialize it to 1 so that when you concatenate the first translation, it just becomes that translation. And then all the other ones are built on top of it. So we initialize to identity. Then for every translation that's added, well, you know what? We don't need all these separate functions anymore because no matter what you do, it's always the same. Apply transformation. Const mate3 and transformation in, and then we do transformation times and equals transformation in, and there you go. This replaces all that other stuff because it's always the same procedure now. Everything is uniform. Remember when I said matrices make our operations uniform? I wasn't kidding. So sexy. So the upside is the interface for drawable becomes much sexier. The downside is now, because we changed the interface, we're going to have to change everything that depends on that interface. That's the price you pay when you're going to do a major refactor. We could have kept the interface the same, and these guys wouldn't have had to change, but then drawable would have been uglier than it could have been. So we want to apply translation, scale, rotate. So instead, what we do is we go drawable dot apply transformation, mate3 rotation angle. That's the last thing we apply. The next thing we apply, mate3 scale by the scale. And the final thing that we're going to apply is mate3 translation by negative position of the camera. And there you go. Now, we're just going to... why are you... right. Because, unfortunately, mate3 translation doesn't take a vector, so we got to go pause X, pause Y. I could make an overload that takes a vec too, but don't care. Don't care about it that much. So, there we go. So now we've changed those 3 lines into a single line where we apply transformation, which is a concatenation of these 3 matrices. Do you get my drift? Camera. So that's one thing that applies transformations. Another thing that applies transformations is Starbro, maybe? Yeah. I feel like you apply a transformation. No, because you inherit from entity. Entity is where all that stuff happens. So let's go to entity, and lo and behold, we've got some red boys here. And again, we're going to apply a concatenation. Again, scale, rotate, translate. A little different order than we did for the camera, and also translation is not negative position, it's positive position. But otherwise, pretty much same shit, different pile. Okay, so far so good. We got the entity, we got the camera. We need the coordinate transformer, which is going to scale independent and translate. Here we go, scale independent, translation. Offset, offset.x, offset.y. Okay, get rid of these guys. Let's go into game. Let's remove this test code, uncomment the actual code, and we'll see if we can build. Probably not. Nope, again, I'm wrong. It works. So, the question is, does it really work? Well, let's put in release because I'm not sure. Okay, well, I think maybe it doesn't really work. What do you guys think? You think this is good, or you think, I mean, it's interesting. It's definitely very interesting, but I don't think it was the effect we were quite looking for. All right, so instead of breakpoint here, let's follow the journey of a star or a star drawable down the pipeline. So we're going to step into this, and that should give us, and the cells of the transformation they look good. 1, 1, 1. So the first multiplication applied the scaling and the rotation, and that looks fine because this looks like a rotation matrix, right? We got the negative here, positive, the diagonals are mirrored, nothing here. That's fine. So this concatenation seems to have worked. Now the second concatenation here, what is this? So we can see here the translation applied afterwards does not affect the rotation, but it should have affected the positioning. So now this should be the position of the star, 241, negative 77. And if we look at this, 153, 160. Okay, so I'm an idiot. I wrote the transformations in the order in which they were in the original code. But remember, this one is going to happen last. But we want this one to happen last. So we actually had to switch the order, at least put the translation before the other guys. So I'm pretty sure I've made that mistake in all of them because I just copied the order. So we fix the order here, put the translation first. We fix the order here in camera, and in the coordinate transformer, we put the translation first, because first is last. So as you can see, this can get confusing and it's easy to fuck it up. So try to keep it in mind that this one, the last one happens first. They happen in reverse order. All right, it's looking a little better, but I still don't really like it. I'm not feeling it. So again, we're gonna step in and we're gonna step over this. We're gonna step in here because we want to see the final result of all these concatenated. And now if we step in, we should get to apply transformation. The transformation in is going to be our actual final matrix, and we get 296, negative 729. So this looks like a rotation matrix. Fair enough. 296, negative 729. Now, if we step out, this 296, negative 729. So now it has the correct position. It looks like it has a valid rotation. So this looks good to me. Looks proper. Let us continue. Return D. Indeed. Get drawable. Return D. So now we've got the drawable and we've got a valid drawable. Now we're going to step in to the draw. It is going to apply transformation of what? Of the camera. So the camera is going to translate it first by the positioning, then rotate and scale. Here's where Git is going to come into handy. We want to compare with unmodified. So in the unmodified one, yes, we apply the translation first. So this one we have to apply the translation first, then we can scale and rotate in whatever order we please. So for this one, how do you like me now? Let's stop this. And let's run again and see if that fixed it. I am very angry. We apply the camera transformation, and now we're going into the coordinate transformer. I'm going to step into that guy. It appears to me now that I have seen the light, and the light is we're applying these transformations. Well, let's go into drawable. So when we apply a transformation to this guy, we multiply. Right hand side is the transformation in, left hand side is the transformation that we want to apply to. But this is a problem. This is a very insidious problem, so let's draw it out for a second. Let's say we got three transformations, A, B, and C. So I start off with identity matrix, and I'm going to do, like I did in the code, I times and equals some matrix. So it's going to be I is equal to I times M. So first one, we're we're going to have I times A, right? Then we're going to take that result, I times A, and we're going to multiply by B. And then we're going to do I times A, B, multiply by C, and this is the matrix concatenation that we end up with, A, B, C. So my desire is to first apply A, then apply B, then apply C. And that seems like what we're doing, but if we look at this matrix concatenation, what we have is we have C, then B is applied, then A is applied, and then I is applied, which is nothing. So we actually get the operations in reverse order because we fucked this order up here. So we would like to be able to use times and equals like this. It would be very sexy, but we cannot. It's very dangerous. So what we're going to do is to save ourselves from doing dangerous things and messing ourselves up, we're going to remove this overload or this implementation directly from the class because it's bad. It's poisonous. We're going to go into the drawable itself and we're going to say transformation is equal to transformation in applied to transformation. So now we put the original transformation, the one that's being built up on the right hand side, multiply that by transformation in. Transformation. What is your problem? Now if we do this, we should get the proper order of application. First the entity, then the camera, then the coordinate transformer. And the order inside of those things I've already fixed. So now you see that it works properly once we have fixed all the orders of the matrices. And it works the same. It should work the same. I can still rotate my camera, scroll around, zoom in and zoom out. Everything works beautifully. And it is now working very sexily, powered under the hood by the matrix representation of transformations. And there you go. That's matrices and matrix transformations in a nutshell. I hope you agree with me in that it's actually not super complicated. It's not an amazingly advanced mathematical topic or anything. It's just a little bit of algorithm, a little bit of loopy. And the only thing I really want you to take away from this is that whole thing about the order of concatenation, because that's probably the thing that you are going to mess up the most when you are writing your own 3D engines. It's very easy to screw up, as you can see, as I have demonstrated. I might normally have cut out all of that debugging, but I wanted to put it in there because I want to hammer home this idea that you got to be careful with your order of concatenation. Not just when you're writing out a single expression, but when you're building up a matrix over multiple function calls. You got to keep that in mind. The only thing that matters is this positioning here, not the order in which you compose this positioning. The last thing I want to say here is that, matrices, of course, we need them for graphics, but that's not all they're useful for. You see them tons of places like, for example, AI, neural networks, convolutional networks, machine learning stuff. Those are all networks. Networks are generally represented by matrices, connectivity matrices. You're also going to see matrices for when you're simulating or analyzing analog circuits, because those are really just networks after all. And all sorts of physical simulations, statistics, stuff like maybe, how Google ranks web pages. Used for encryption all over the place, you got matrices. So don't get the idea that matrices are only really used for 2D, 3D graphics. And also don't get the idea that matrices are all just, 3x3 or 4x4 square matrices. Because in, for example, neural networks, convolutional networks, you're going to have huge matrices. And you've got pieces of software that are dedicated, pieces of software and hardware that are dedicated to crunching these huge matrices. So just know that matrices have lots of applications outside of graphics, and it's well worth your while to learn how they work. And that's going to about do it for this video. And actually, I want to say congratulations, you have made it to the end of math time. So this sequence of basically this arc of 5 tutorials at the beginning of Advanced, all the stuff that's basically needed in order to start 3D fundamentals. So if you have completed these videos, if you've understood the material to a decent degree, you should be ready to begin your journey into 3D fundamentals, which will lead you onto hardware 3D in the future. So go on to that. But also keep in mind that I will be continuing on creating advanced C++ videos in this playlist, and they are going to actually be about C++ topics now, not just math that is implemented using C++. So look forward to more advanced C++. Go ahead and start 3D fundamentals if you haven't already. That is your homework. As always, thanks for watching. Hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more advanced C++ and 3D fundamentals.